Alright, so with 4.6 we're going to talk about related rates, and we're going to spend a couple of days in class as well working on this, not only the assignment that you'll have for but also some examples that I'll help you work through and talk more about. And this is probably the second most important thing about the applications of derivatives that you're going to learn in this chapter. The greatest being, of course, maximums, minimums, and optimization, but related rates are right up there with it. And what we're doing is we're looking at how the rate of change of one thing affects the rate of change of another. So let's start off first with a review problem. Let's look at that problem that we looked at in 4.5 with a sphere of radius 10 centimeters, and it's changing. The radius changes by 0.1 centimeters, and how much does the volume change? Well, if you remember, we actually did this, worked it out, and we took the derivative of both sides with respect to r, multiplied both sides by the dr, because over here we'd have dv dr, multiplied both sides by dr to get it off the bottom, and we end up with this. So the change in volume is equal to 4 pi r squared dr. So then, of course, when we plug everything in, we found that our change in volume was 40 pi cubic centimeters. Well, that is approximate. We learned that that was an approximation and that the volume would change by approximately 40 pi cubic centimeters. The reason why is this. We're treating dr, which is supposed to be a very, 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 very incredibly tiny, small amount, but 0.1 centimeters is not. So the larger that gets, the more inaccuracy you add to it. So we're finding that this is an approximation, so it's changing by approximately 40 pi cubic centimeters. And that's what happens when we do a differential. Now, what we're talking about today is a related rate. Now, suppose that that radius is changing by an instantaneous rate of 0.1 centimeters per second. Now, the number's still the same, but at that instant in time, super tiny instant in time, we know that we're measuring this to be changing at a rate of 0.1 centimeters per second. That makes all the difference in the world to the final answer. So, for instance, if we had a sphere or that's a soap bubble or a balloon that we were blowing up, well, then if we calculate it, we're going to take the derivative of both sides with respect to t, not r, because we're doing the per second. This is a rate of change. Before, it was just an amount of change. There's a difference in that when we're talking about calculus. So it has to be a rate of change of one thing with respect to another. So when we do that, we've got dv dt is equal to 4 pi r squared dr dt. Then when we plug everything in, we're still going to come up with that exact same 40 pi, but we're going to have cubic centimeters per second. Now, what we've just found is not approximately how much the volume changed, but we found the rate of change of the volume at that moment in time. That's the difference. So it has to be a rate with respect to, in most of the instances we're going to look at, it's going to be with respect to time in some way. But this is actually an exact measurement. So if we're finding a rate of change, then the calculations are going to work correctly. Alright, so let's look at another example. Water is draining from a cylindrical tank with a radius of 10 centimeters at 3 liters per second. How fast is the surface dropping? So what we're looking at here is we're looking at, there's water in this tank, and let's say that's the level that it's in. Water is coming out in some way. Yes, it's purple water. And when that happens, what's going to happen to the surface level of this liquid? It's going to go down. So that's what we're actually looking for. So we're looking for dH dt, where h is the height of the liquid. So that's what we're looking for here. And what do we have? Well, we know that the radius is 10 centimeters. Now, an important part here is the fact that what do we know about the 10 centimeters? Does it change from this level to this level to the bottom? No. With a cylinder, the radius is going to stay constant through the whole time. So this is a constant, which is important. So if it's a constant, that means that we're not going to differentiate the r when we take the derivative. If it's not something that changes, we know that there's not going to be a rate of change. So if you were to do this, actually I'll talk about that in just a second. All right, and then what do we know about the 3 liters per second? Well, that is your dV dt. Now, with the liters here, liters and centimeters don't play real well together, so you're going to have some way that you can get common terms that can cancel out. Well, if you remember, back in the optimization, we learned that a liter is 1,000 cubic centimeters. So this is 3,000 cubic centimeters per second. And that's what we're going to use. That way we can actually cancel out when we need to and all that. Now, the volume of a cylinder is pi r squared times h. Now, once again, like we said, when we talk about this 10 centimeters being a constant, if we take the derivative of this, we're going to get a dr dt as well. Well, the dr dt, since it's not changing, is going to be 0. So we actually don't have to take the derivative of that at all. If you do, if you used the fact that you treated it as r squared and h were both changing, and you did the product rule here, when you put the dr dt in there as 0, it cancels out what's not important. So if you make that mistake, it's okay, as long as you remember that your radius is not changing. But since we know it's not changing, we can treat this just as a constant, just as it is, and leave it as it is. So when we take our derivative, we're going to get dV dt is equal to pi r squared, not taking the derivative of that, and then the derivative of h with respect to t is going to be 1 times the dH dt. That's that conversion factor to convert the derivative with respect to h into a derivative with respect to t. So now, when we solve this, we're looking for dH dt, so when we solve it, we're going to find that dH dt is equal to dV dt over pi r squared. So when we plug everything in, we're going to have 3,000 cubic centimeters per second divided by pi times 10 centimeters squared. So now look at your units. What are we expecting this change in height to be? Well, dH dt, since our measurements of length are in centimeters, this should be in centimeters per second. Is that what's going to happen here? Well, when we square the 10 centimeters, we're going to get centimeters per second down there. Divide that into the centimeters cubed per second, we're going to get centimeters per second, which is exactly what we want. So supposedly, looking like we've actually got this thing set up correctly. So when we do the 3,000 divided by 100 pi, we're going to end up with 30 over pi centimeters per second. And that's going to be your rate of change of the height with respect to time at that instant in time when 3 liters per second are coming out. Alright, so here's the steps you need to go through for a related rate problem. First thing you need to do is you need to draw a picture. It does not have to be a pretty picture. You've seen my drawings. They are not pretty. But you need to be able to visualize what's going on. So draw a picture, label the things that you know, Also label the things that you're looking for. Write down all your known information. Write down what you're looking for. Write an equation that relates the variables that you're dealing with. Then you want to differentiate both sides with respect to t, plug in your information, and solve. A lot of people will skip the draw a picture. Guys, it's going to help you so much if you'll draw a picture. Alright, so here's a hot air balloon problem. We've got a hot air balloon here that is 500 feet away horizontally from the person that's watching it. We're given that theta is pi over 4 and d theta dt, in other words, how this radius or this angle right here is changing, is 0.14 radians per minute. How fast is the balloon rising? Alright, so we're relating the opposite and the adjacent. So that means we're dealing with the tangent. So the tangent of theta is equal to h over 500. Which you could also think of as 1 over 500 times h. Now we want to take the derivative of both sides. The derivative of tangent theta is going to be secant squared theta d theta dt. And then on this side, it's going to equal 1 over 500 times h, or just 1 over 500 times the derivative of h, which is dh dt. So we know what d theta dt is. And we know what this side over here is. We're looking for how fast is the balloon rising, so we need to find what dh dt is. So that means we're going to multiply both sides by 500. So dh dt is equal to 500, when we multiply this to the other side, times the secant squared theta times d theta dt. Now, you're probably freaking out here, and you're saying, okay, well, how do I deal with that secant squared? Well, the thing is, we're given the angle right there. At pi over 4, what do we know about this side and this side? Well, we know that the related sides, if we draw a triangle, that's a 45-degree angle, 45 here, 45 here. We know that this is going to be 1, this is going to be 1, and this is going to be the square root of 2. That's your 45, 45, 90. You could also think of it as 1s, and s times the square root of 2. But that's the relationship between those sides. So now, what is secant squared? Or what is secant? Well, remember that secant theta is nothing more than 1 over cosine theta. So if you wanted to deal with cosine, remember cosine is adjacent over hypotenuse. So in this case, if we had pi over 4 here, let me erase that where it's actually visible. That's going to equal 1 over the square root of 2 on the bottom. Sorry, that's wrong. It's going to be 1 over, the cosine is going to be adjacent over hypotenuse, so it's going to be 1 over the square root of 2. Which is of course, just the square root of 2. So that means the secant is the square root of 2, coming from the special right triangles. So dH dt is equal to 500, that's feet, times the secant squared, or square root of 2 in this case, squared, times your d theta dt, which is going to be 0.14 radians per minute. Now when you look at your units, see if it's going to work out. Here's where you got to remember. Radians are technically not a unit. They're a ratio. So the radians, while they're not really there. And what happens when we multiply feet times per minute? We're going to end up with feet per minute, which is what? Pretty much what we're expecting this rate of change of h to be. Then when we multiply everything out, 500 times the square root of 2 squared, well the square root of 2 squared is just going to be 2. That's going to give us 1,000 times 0.14, which gives us 14 feet per minute. Just kidding. It's actually 140 feet per minute. Because we've got 1,000, that would move the decimal place 3 places. So 1, 2, 3, 140. So that is how fast the balloon's rising. That's moving pretty fast. I don't want to be on that balloon. Alright, one more example. And this is the truck problem. Truck A travels east at 40 miles per hour. Truck B travels north at 30 miles per hour. How fast is the distance between the trucks changing 6 minutes later? Alright, well remember that rate times time equals distance. The only problem is here we've got hours, here we've got minutes, so we're going to have to convert one of these to the other. We're going to convert the minutes into hours. That's going to be 1/10 of a minute, of an hour, sorry. So 40 times 1/10 gives us 4. So this is 4 miles per minute. And that's the distance in that direction to the east. And 30 times 1/10 gives us 3. That's going to be the distance going north from the same start. And this dotted line right here is what we're looking for. We're looking for what that change is going to be. Let's go ahead and call that Z. So we're looking for dz dt. Now, what is z in this case right here at that moment in time? Well, it's 5. 3, 4, 5, Pythagorean triple, so we know that. So this is 3 miles, 4 miles, and 5 miles. Now, what's the relationship between these three variables? Well, Pythagorean theorem. So we know that x squared plus y squared equals, not 5 squared, but z squared. We can't write 5 because, what do we know? As these trucks are moving, this z is changing. So since it's changing, it has to be labeled as a variable. So then when we take the derivative here, we're going to get 2x dx dt plus 2y dy dt is equal to 2z dz dt. And that right there is what we're looking for. That's what we're solving for. So we've got a common 2 that we can get rid of. We can divide both sides by 2. There's a common 2 on this side to factor out. It'll divide with that 2 right there. And then to find the dz dt, all we have to do is divide both sides by 2z. So dz dt is going to equal x dx dt plus y dy dt, all divided by 2z. Now, when we plug everything in to that, x was 4, dx dt was going to be 40 miles per hour, plus y, which is 3, times dy dt, which is 30, and divided by 2 times z, which is 5. So we end up with 160 plus 90 divided by 10, and that's going to give us 25. Now, what's our units here? Well, remember, this was miles. This is miles per hour. Miles, miles per hour. And then this would be miles. So what happens up here on top? We get miles squared per hour plus miles squared per hour. That means we can't add them together. Guys, if they were not the same units, we can't add those together. And then if we have miles squared per hour divided by miles, we end up with miles per hour. So that's the answer. Now, guys, let me talk to you a little bit. There's going to be problems where z is changing. There are also going to be problems where z is not changing. For instance, you're going to see a ladder problem where the ladder is leaning up against a wall, and we know that the bottom is sliding out at a certain rate, and we need to find how fast the top's coming down. Well, the ladder is not changing length, so if they told you that it was a 15-foot ladder, it's still going to be a 15-foot ladder when it's laying flat on the ground. So in some cases, the z is not going to change. In that case, way back to right here, you can just put 15 and be done with it. When you take the derivative of that side, you don't have all this. This would be 0. So be aware of whether the variable and all the parts are changing. Anything that's changing, you have to leave as a variable and differentiate it. If you don't, you're going to get the wrong answer. Bad, wrong. So make sure you know what's changing and what's not. And there are also going to be situations where more than one thing is changing. You're going to have to find a relationship between the two. For instance, if you deal with a cone that's leaking water, red water in this case, and you're looking for how fast the level's going down, well, the problem with this is that makes it a little more complicated is what happens as you get down to this level. Well, not only has the height changed, but the radius has changed as well. So you've got to find some way to relate the height of the water level with the radius. And we'll talk about some of those as we do some problems in class. Not all of them are that complicated, and you'll be able to do them. But until we actually talk about some, you can actually start on some of these and work them out. All right, that's all for this section.